Okay, physical science time. Today we are talking about science and measurements. This is a science class, and so it's probably important that you know what science is. However, I think that you probably came in here with at least some knowledge, however lackadaisical it was, of what science is in general. But we're going to talk about how science relates to society and how science relates to math. It's kind of really, that's kind of even the point of this class. We talk about similar topics, many of them the exact same as last year, except for now we talk about how they are, how they relate to mathematics. So let's write down the objective, which I just wrote over here, and it's explain and utilize measurements in science. Explain and utilize measurements in science. Okay, you know how this goes. We've done this at least 14 times before. What is the first thing I'm going to ask you? I'm going to ask you a question. That's how we start these discussions usually. What do you think that question is going to be? This is cute. You can see if you can remember. Go ahead, Avery. Say it loud. Say it. What is science? Yep, I usually just pull this little guy down and ask you to define it. So in your own words, did you guys do vocab for this chapter already? Yeah. So not the vocab definition that you wrote, but in your own words, what is science? Do not listen. Don't tell me what you wrote down. Tell me in your own words, what is science?
It was bell work. Yeah, it was bell work.
Bell work? You just want me to write the word bell work?
No, you made us.
Science is all about bell work, and that actually does seem to be the truth in this class. But what is science? Define science for me as, yes, Isaiah, let's hear it. Okay, let's start with that. Laws defining how the world, I like that, functions. There's a couple things that I really like about it, and there's a couple things that I wouldn't say I don't like, but that I'm worried people might have misconceptions about, so we're going to be more specific. But I like that. Laws defining how the world functions. Let me ask you a couple more questions. Actually, let's just do this right now. In your vocab, you also had the idea of a scientific law versus a scientific theory. Let's just talk about that right now. That was actually going to be a little later, but since Isaiah defined it this way, which I really like that definition, let's talk about the difference between these things. So both of these are in science. In your normal day-to-day walking around and going and get ice cream and branding cows life, these things have different meaning from what they have in science, but not a very different meaning. So in our normal life, I even too have been called a normal person before. No, that's not true. No, you got me twisted. I am not. I am totally abnormal. God broke the mold when he made me, and that's true for you too to some extent. But a law in our normal life, in so much as we have such a thing, is a set of guidelines, a set of rules that you have to follow, or else the police shoot you. And a theory is something that you might say, basically the way we use theory in our daily life is a guess. We basically mean guess. Like you or your mom might say, I have a theory that they're out of yogurt at Walmart. And that's, you don't mean theory in the same way that we mean theory in science. And so your familiarity with these terms is actually a little bit of an impediment to you. But in science, a law is an observational truth. So let's write that down. I think these are vocab words, and so I should probably ask you them. But a law is an observational truth. That means that we observe it to be true every time we observe it. Give me an example of a scientific law. Gravity. That's the one I was hoping you'd say. Meaning that every time that we observe gravity, it does the same thing every time. And someone said it goes down. You can see I'm getting posed to drop this. Because hopefully you know a little bit more about gravity than that, we probably could be more specific and say that this will be attracted toward the largest, closest mass, right? Is the Earth the largest mass in the universe? No, but it's the largest, closest mass. And so when I drop this, it's going to be attracted to planet Earth. And it is. Every single time. It's an observational truth. We observe that to be true every time. I could drop either of these markers or my coffee cup or whatever. I could drop everything, anything. I'm not going to answer that. Anything I could drop 1,000 times, and it would happen the exact same way, right? That's an observational truth. It is true that that's going to happen, and it happens every single time we observe it. A theory, though, is, and this is usually more, I wouldn't say more important necessarily, but it's an explanation. So instead of where the law of gravity is that going again?
Yeah.
Okay. So while this is an observational truth, that if we drop something every time we observe that it's attracted to the nearest, closest, largest mass, an explanation would be why does that happen? And that's usually, one, more complicated, and two, much more useful in science. So why does this marker be attracted to planet Earth? That's a much more difficult question. It's actually a question that science is kind of actively trying to solve. Why does gravity exist at all? And so you can see that that's much more important, or at least it's much more fundamental. It's much more foundational to the universe as to why it's happening than just the fact that it does happen. So those two things are different. So I don't dislike that Isaiah said that it's the laws defining how the world functions. It is that. It's a description of how the world works, but it's more than that. It's usually at its best, or it's usually at its fulfillment when it's a theory, when it's an explanation. And this, again, is different from how you use theory. This is not just a guess. This is an explanation based on all available evidence. So all of the evidence collected, maybe back referring to this law, all of the evidence collected says that this does happen, but why? Well, we have to look for more evidence. We can't just keep dropping things and that will give us an explanation. That will tell us why. We have to look at more in depth. We have to look at, for instance, the particles. We have to look at the movement of anything that has mass. And it's based on all available evidence, and this changes. A lot of times it also has to do with a scientific model. You remember a model? You probably know a model. How do we use the word model in our daily life? Girl. Doesn't have to be a girl. But yeah.
You said this person.
Yeah, it's a person who shows you what clothes might look like on you. When I was growing up, that wasn't true. It showed you the very best way that clothes could look on you. But now they do have some. I've seen them. The models themselves, no. But I've seen the pictures on packages at Walmart, and they actually do a better job now compared to when I was a kid of having people that look like the shape of other normal people on them. But they show you how the clothes might look, right? They represent. A model is a representation. A model of clothing represents how those clothes might look on another human being. A model in science represents how, for instance, the world looks. You see the globe? I'm indicating the globe. That's a model. Is it, are either of these things, let me give you an example. If a new mountain grew on planet Earth, which does sometimes happen, a volcano erupts and there's a new mountain in the middle of the ocean, would the globes that are made after that indicate that there's a mountain there? Probably. The globes made after it? Yeah, why wouldn't they? I mean, if we discover a new island, of course the globes that we make after that would have the new island on them. So the model can change, and the model is imperfect. Does that globe perfectly represent how the world is? No. How can you tell? It's not big enough, yeah. But now listen, would that be a useful model if it was big enough? No. If that globe was the size of the actual Earth, it would, one, not fit in my classroom, and two, it would have a lot of other problems that people would have to deal with, like their houses burning down because the world exploded. So is it a strength or a weakness that the model is just a representation? It's a strength. Like, we can represent things that we otherwise couldn't see or observe with a model. And is it a strength or a weakness that models and therefore theories can change? That's a strength too. A lot of times in your little cowboy life, you think that changing is weakness. Like, if your dad says, "Oh, I changed my mind, you can go to prom," you would see that as weakness in your dad. But in a scientific model, in a scientific theory, that change is actually a strength. It's something like admitting, oh, we didn't quite have this right. We're going to change the model and therefore change the theory. So that's a strength of science. And then the last thing that Isaiah says is how the world functions. Here, I want to, this world, I'm going to change that to universe. A lot of times, and I will do this too, a lot of times we use the phrase the world to mean everything. Everything. And so probably a better name for that is the universe. But the root word for universe is one. It is all one. Everything is one, and it all kind of goes together. And then how it functions, the only problem I have with this, Isaiah, the whole line, the only problem I have with it is that function kind of indicates that things have a job to do and that they're working towards some designed end, which even, that may be true, but that's not really the point of science. It's not how things work in the sense that I work at Crawford High School, or that, does any of the rest of you even have a job? Probably not, but it's not that kind of work. Isaiah works at Seas. It's not that kind of work, but I agree with that things do act. Let's put acts here instead. So that's science, kind of in a nutshell. Some of the ways we describe that are with the SEPs and CCCs that we have talked about last year. You see those posters over there? Make sure you remain familiar with those. I'm not going to go over them in this discussion because we're running out of time, and because I expect that you already know them from your labs last year. And so we'll just be aware we're going to continue to use those. If you need more information, or if you're like watching this video to study for your test and you know they're going to be on there, which they are, I have another video that I made for the 8th graders that includes a discussion of those. And so if you want to learn about those, you can. However, in this talk, we're just going to be talking now about measurements. So we're going to switch to measurements. So measurements are important in science because they're a way that we can, I'm trying to think of a good verb for this. I'm going to put, this is going to be a little cute. We're going to explore with numbers. So this is a way that we learn about the world, a way that we explore the world is by comparing the numbers of things. Human beings love to categorize and measure. The world in reality does not exist in categories. Human beings categorize it. The world in reality does not exist in numbers. Human beings apply numbers to things. And categorizing and measuring are the tools of science. And that can, kind of like models and changes, or models and theories, that can be seen as a weakness, but it's actually a strength. And so the best scientists, which some of you guys are and are becoming, the best scientists, that is people who do science, people who learn about the world, categorize and measure without forgetting that the universe is all still one. Like we can say that this is cup and this is saucer, but they're also one set of cup and saucer, right? Or this is Allison and that one's Chloe, but they are all one part of the species called Homo sapiens. And so we remember that we define them by their differences, but we remember they're all fundamentally one thing. And so we explore with numbers in the form of measurement. And now let's talk about that. In science, we use what's called the SI, which is from the French for système. I think the accents go like that. International, which is like the word international in English, but with an E at the end. D'unités, which is like of units. So the international system of units. We usually just call it the SI. Sometimes we call it the metric system, although that's not technically true. But we use this system of 7 base units, and then we add prefixes or suffixes or combine them. And so the 7 base units that you need to know are, you don't need to know the 7 base units, but the base units that you need to know are the meter, which measures what? What physical quantity does it measure? Length. Length or distance. They're the same thing, but we categorize them differently. Length or distance. We do not use inches and feet in science. It just isn't done. That's not because those things are wrong or because they're less precise. They can be every bit as precise. We just don't use them in science. There's a different time and a different place for everything. Meters, we use let me do this one next, actually. We use seconds to measure what quantity? Time. Seconds and its derivations, minutes and hours, days, etc., to measure time. we use a temperature scale called Kelvin to measure temperature. Kelvin. It's named after a man who was, his peerage in England was Lord Kelvin. And so, but that doesn't really matter. It's just that we use this to measure temperature. And we'll talk more about this when we get on into chapter 5, I believe, in the book, which is about thermodynamics. But we have meter for distance or length, seconds for time, Kelvin for temperature. I'm trying to think of the other one that we use in this class. Does anyone? Newtons are not a base unit. Oh, kilograms. Yep, you're right. Kilograms is the other one that we use. Kilograms measure mass. Now you'll notice that this one does have a prefix, and it's considered the base unit because kilograms is generally a more useful unit than grams. Grams are really quite small. And so then, based on these base units, we either combine them there are 3 others, amperes, candelas, and moles, but we're not going to use those this year, and so you don't really need to know them. Oh, actually, I should include amperes because we will use that. Amperes are a measure of electrical current. So there are 7 base units, and all the other units that we use in this class are based on those base units, which we would call derived units. I think that was one of your vocab words. So we derive other units from these base units, and one way that we derive them is that we add prefixes. So what is the prefix? Let's start with the smallest one we will commonly use in this class is milli. And what does milli represent? Well, it could be milliliters, it could be millimeters, but the point is we can add milli to any of these or other things. But it's what fraction? 1/1000th is exactly right. Good. We use centi, kind of like the word century, to represent what fraction? 1/100th. Then we have the base unit, and then we use the other main one we will use is kilo, which is what? Well, kilograms do exist. That would be how many grams? Nope. 1,000. Like if someone says they make 10K, the K stands for kilo. And in that case, they're talking about kilo dollars, which you would never say, but the K means 1,000. Kilo means 1,000. So 1,000 times that quantity. So we could have kilograms already has that, but we could have a kilometer, a kilometer would be 1,000 meters, right? We could have a millimeter, which would be 1/1000th of a meter. And then we also do combine them. You can, from our bell work, you'll realize that we had, the answer was, doesn't really matter, but 0.891, I think, grams per milliliter. Do you see how this unit, grams per milliliter, is derived? A gram is 1/1000th of a kilogram, and a milliliter is 1/1000th of a liter, which itself is defined as a cubic decimeter, which is 1/10 of a meter. So this unit, grams per milliliter, is made up of these, as all units in the SI are made up of these and moles and candelas. The thing that we do with these measurements, and this is where we're going to have to go through this really fast, but there's this process that we do called dimensional. You need to write this down. This will be the most important thing that we do. In this class, unlike last year, if this was last year and you guys were 8th grade, little puny little 8th graders with your stinky smell and your bad attitude and your poor intelligence, we would be done. But now we're going to talk about the math that we're going to actually do for this chapter that will be your worksheet, that will be due on your chapter review, and that you will have to have done by Friday. And we call this a dimensional analysis. Almost every unit, I think every unit in this curriculum except for one, has some math activity for you to do, and today's is called dimensional analysis. Referring to what? What's an analysis? Yeah, you look at something and you try to figure it out. That's an analysis. Okay? If you're doing an analysis of a dog's intestines, you would be like poking around in there and like, oh wow, this dog ate a mouse or whatever. I don't know. I probably could have picked a better example. Dimensional means referring to what? Dimensions. Referring to the measurements. This is how it starts to look like a crazy person is teaching you. Dimensions are another name for measurements. So the dimensions of, I don't actually know anyone's dimensions, but sometimes you talk about a person's dimensions. Like I'm, in the English system, I'm 6'1". That's about 182 centimeters, which is 1.82 meters. My chest is 40 inches around, and those are measurements that I have that I use to buy clothes. My waist is 30 inches around, my legs, my inseam is 31 inches long. These are measurements, they're dimensions that I use to buy clothes. I only know those, not because I'm a weirdo, but to buy clothes. I think girls, when you buy clothes, pants, they're just numbers, right? Like 2 or 10 or something, and no one understands. You just have to figure it out. But when you're a boy, when you're a male, the pants just say their size in inches. They say 30 by 30. You're like, oh, those ones will fit me. And then you just know. You don't even have to try them on. You just walk out of the store with them. You pay. If you're into that, you pay first, and then you walk out of the store. But dimensions, my point is dimensions is another name for measurements. Dimensions is another name for measurements. So dimensional analysis is looking at the measurements of things and kind of poking around in them, and that's how we do our math. I'm going to do a very easy example, but they have to be set up like this. So we had in our bell work a way to set up equations that I hope you're getting familiar with. We're going to be using all year. But we're also going to be doing this method of dimensional analysis, also sometimes called, I call it, unit conversions. What's a unit? Yeah, a way that we measure things, a system that we use to measure things. And what's a conversion? Who said change? Good. Changing one thing to another. So we're converting from one, and you might have said that too, Amelia. I just didn't quite hear you, and someone over there was louder. Changing from one thing to another, we call that unit conversions. And so there's a right way to do these and a wrong way. And I'm going to tell you straight up, right out in front, at first these are going to seem like I don't need to show my work, this math is too easy. But this is a very good example of if you don't learn this when it's easy, by the time it gets hard, you will not have a cotton pick and clue what's going on. And so we convert units from one to another, and we do that by first writing them. Let's say that, like me, we're talking about a quantity that is 6 feet, and we want to find out how many inches that is. Okay, that'll be easy. So 6 feet to inches. The first thing we do is we write our given. 6 feet. That's the given. Have you heard that term given before? Ooh, that was dangerous. I almost lost the life of my beautiful teacup. So we start with the given. Then we do this, what I sometimes call a fraction bar. Sometimes I'll call it a unit conversion bar. But it's basically we're multiplying it by a fraction. Okay? We're going to be multiplying it by a fraction. If you're not writing, you are going to be so bad at this class that you can't pass it. 6 feet, and we're going to multiply it by some fraction. And that's going to give us some other number. So first write the given, then we're going to multiply it by some fraction, and the fraction we are going to put in the bottom. What's the correct name for the bottom of a fraction? Denominator. We're going to put in the denominator the thing we want to, the unit we want to get rid of. So we're currently talking about feet. We don't want to talk about feet anymore, so we're going to get rid of it by putting it in the bottom. Do you see already that if this were algebra, which it is, if this were algebra class, which it ain't, but if this were the process of algebra, which it is, having this variable ft here and in the bottom, what's that going to do to the variable ft? Get rid of it. It's gone. And we're going to go to, I use the phrase go to, we're going to put in inches. So in the numerator, we put inches. Now, what number should I put on these lines? Well, this fraction must be equal to 1 because we're not trying to change the value. So we're going to be basically multiplying it by 1. So in 1 foot is equal to 12 inches. These two things must be equal. 1 foot is equal to 12 inches. And then, the easy part, we just multiply by the numerator, divide by the denominator. So in numbers, we have 6 times 12, which is 72. And divide by 1, still 72. And then in units, we have feet in the numerator, divided by feet in the denominator. So those, Mr. Snilly does not want me to say cancel out, and he's right. Reduced to 1. Feet on top divided by feet in the bottom. Feet in the numerator divided by feet in the denominator means 1. They reduce to 1. And we're left with this unit, inches. And the last step is we check, would it make sense for a dude or a piece of PVC pipe or a 2x4 or a tree that is 6 feet to be 72 inches? Well, yeah, we have, you see, if this is 1 foot, would it make sense for 6 of those to be 72 inches? Yeah. So the last step is you check for reasonability. Now, if you're used to units at all, you'll realize that this math seems a lot more complicated than just multiplying in your head 6 feet to 72 inches. But if you don't do it like this when it's easy, by the time it's hard, you can't do it at all. You have to type into Google. Don't do that. These get a little bit more complicated. There are 2 ways that they complexify. One is that they can be chained together. So like if we were instead going to centimeters. We'll just do this one together real quick, and then I'll tell you the other two, and we'll do those when we go over our worksheet. But since we have time, and we can use this for video evidence, we'll go to centimeters instead. So 6 feet, again, we start with our given. 6 feet, draw our fraction bar. We're going to get rid of feet. How many centimeters are in a foot? You don't know. How many inches are in a foot? You do know that, so we're going to go to inches. And then how many inches, or how many centimeters are in an inch? You also don't know that, but you're about to, because I'm going to tell you, you need to have this memorized. In 1 inch, there are 2.54 centimeters. You must memorize this. This needs to go in your brain. This is the best way to convert from the SI to the English system almost always. And so memorize this conversion factor. Once you have that memorized, you realize that just like there are 12 inches in 1 foot, there are 2.54 centimeters in 1 inch. We do the same thing, except now they've been changed. So it's 6 times 12, sure, 72, times 2.54, which you would need a calculator for. But I'm going to just real fast say it's going to be 144 plus 36, which is 180. It's going to be about 180. It might be 182. I already know it is. Because remember I told you that's my height centimeters. So we have, and then we go through our units. Feet reduced to 1, inches reduced to 1. We're left with centimeters, 182 centimeters. So this is how we chain them. We can go not only from one unit to another, but from one unit to another to another. The other way that they get more complex is that sometimes we have rates, which means that there's a unit in the denominator already. Same thing, except we would use the numerator to get rid of that unit. And if we ever have a squared or a cubed unit, we have to get rid of that as many times as it is there. So if it's centimeters cubed, we have to get rid of it 3 times. I think that's good. This is pretty much the fastest I've ever done, so I think you guys are actually really good students, although I would never say that on video. I don't want anyone to tell me that again. But I think you can do a really good job of this. Do you have questions? First, do you have questions about how to perform dimensional analysis? Write the given, write the fraction, put the units in, put the numbers in, and then multiply. Do you have questions about what sciences and what measurements are useful for? It sounds like you, instead of having questions, you have baggage to pack away, so I'm just going to go. Bye.